All right, so let's try to justify the power rule. So in order to justify the power rule, to show that this right here is indeed true, I have to use the limit of the difference quotient. So the derivative with respect to x of x to the n, I have to use my limit as h approaches 0 of f of x plus h, which would be x plus h to the power n minus the original function x to the n all over h. And the problem here is that n could be 1 or 2 or 10 or 1,000,000. I don't really want to take this to the, multiply this out 1,000,000 times. That sounds painful. So to do that, we're going to go back to an algebraic idea that you may or may not have seen in pre-calculus called the binomial theorem. In algebra. Turns out there's a binomial theorem in statistics too. So I want to emphasize this is about algebra here. And what the binomial theorem tells us is, I'm going to write it in the form, we have this thing a plus b. That's a binomial. A binomial is when you add two things together, and then we raise that to the power n. And it turns out there's a pattern to how this multiplies out, right? So what does that mean right there? Well, it means take a plus b times a plus b, and you just keep doing that until you get n of these. Oops, that's supposed to be b right there. Right, so I have to have n of these written out. And then I start multiplying them 2 at a time. Oof, that's a lot of work if n is a big number, like 100. Oh my God. Now, the shortcut to this right here to figure out what that pattern is to turn this into a standard polynomial is what's called Pascal's triangle. And Pascal's triangle is this beautiful work of mathematical art where there's a 1 at the top, and then underneath that, there's a row of 2 1s. And underneath that, the pattern goes, there's always a 1. To get the next number, you add the 2 numbers above. So this 1 plus that 1 is 2, and there's always a 1 at the end. Right? So the rule to keep generating rows of Pascal's triangle is you always have a 1 at the beginning and a 1 at the end, and otherwise the numbers that come next are from the sum of the numbers above. So, and the number of things in the rows, it always goes 1 thing, 2 things, 3 things, 4 things. All right, so the next row would be a 1, and then 1 plus 2 is 3. 2 plus 1 is also 3, and then there's a 1 at the end. And I'm going to generate another row, start with a 1. 1 plus 3 is 4. 3 plus 3 is 6. 3 plus 1 is 4, and then there's a 1 at the end. All right, so why do I care about this? Well, I care about this because this row right here is n equals 0. This row right here is n equals 1. This row right here is n equals 2. And this row right here is, guess what? N equals 3, n equals 4, and so on. And these numbers tell me the coefficients of a and b in the multiplied out version. So let's just think about a simple one like a plus b squared, which we've done a ton of times in our mathematical lives. That's a plus b times a plus b. And we know that's going to give us an a squared plus an ab plus another ab. So that's 2 ab's plus b squared. And here's my 1a squared, 2ab, 1b, which is this row right here. Let me highlight something here. All right, so these coefficients, 1, 2, 1, are these right here, 1, 2, 1. So if somebody asks me, hey, what is a plus b to the 4th power? Notice up above, there's an a squared, then an a to the 1st power, then no a. And going the other way, there's a b squared, b to the 1st, then no b going the other way. So this is going to start off with an a to the 4th, and it's going to be just one of them. And then plus comes next. If that's a minus in between, it's a little trickier. The signs alternate, but it's not bad. This says the next coefficient is a 4. A's power drops down 1. B was, there's no B there, so there's got to be a B to the first next. And then next coefficient is 6. So there's going to be a 6. A's power drops again. So that's going to be A squared. B's power rises to B squared. Next, there's going to be a coefficient of 4. A's power drops again. B's power rises. And then finally, the coefficient is 1. A's power drops from 1 to 0, so the A goes away. And B's power rises, so I get a B cubed. Right, so that's a pretty fast way to take a binomial and raise it to a power without having to do all those intermediate distributions, knowing this pattern. Okay, so how does this work? Like, it keeps going, but it turns out in addition to these numbers coming down from the ones above, they're related to another special mathematical thing called a combination. And a combination is a way of counting things. So if I jump down here to the row where I just call it n, the first thing in the list is going to be a 1. The next thing in the list is always going to be n, right? 1, 2, 3, 4, whatever n is comes next. On the other side, it's going to be pretty similar. The question is what happens in the middle here. At the end, there's going to be a 1, and there's going to be an n. Right, and this here is the nth row, given that I start with row 0 at the top. And to get the ones in between, the formula looks like n factorial over what I call k factorial times parentheses n minus k factorial. And I'm going to work one of those out here in just a second. Factorial, right? What the heck is a factorial? So hopefully this is math you've seen before. If it isn't, then you're just getting a hell of a workout today. So factorial is a product of descending whole numbers. So for example, 5 factorial is 5 times 4 times 3 times 2 times 1. So like in this example up here, my n is the 4. 4, n equals 4. What's the k? So the k is a counter that goes across the row. So n counts which row I'm in, k counts across the row. So k counts across, where n counts down in the Pascal's triangle. So I have k equals 0 here, and then k equals 1 is this one, and then the next one would be k equals 2, and all the way down to the end here where k would be equal to n exactly. So if I pick on, say, this coefficient right here, that 4, n is equal to 4 there, and k would be equal to 1 there. And if I apply my formula there, n factorial over k factorial times n minus k factorial, then I get n is 4 times 1 factorial over 1 factorial times 4 minus 1 would be 3 factorial. That's a factorial. And factorial just means multiply by the numbers below. And so some things to note, 1 factorial is just write down a 1. And it turns out there is a 0 factorial, and it is also 1. This is an important, not obvious idea. And we just call it that because otherwise things don't work out so nice if we don't call it that. So what's 4 factorial? 4 factorial is 4 times 3 times 2 times 1. What's 1 factorial? It's 1. What's 3 factorial? It is 3 times 2 times 1. And the cool thing about this fraction right here, let me do that in a different color. I guess I have it written over here too. This fraction right here, it's always a whole number. Always, which is pretty damn remarkable. The 3's divide out, the 2's divide out, 1 divided by 1, who cares, divide by 1, who cares. So the answer is 4, just like I claimed it was up there. Okay, so what's the point? The point is I need Pascal's triangle to multiply that out quickly. in order to do this. So let's go about it. Next page. According to Pascal's triangle, my step 1 of my process is what the heck is x plus h to the nth power? And according to Pascal's triangle, it's going to be 1 x to the n plus n times x to the n minus 1. I drop the power of n, and h jumps in. H is like my b before. Next, I get coefficient. So I'm going to go off to the side here. N factorial. These are my coefficients. Coefficients over k factorial times n minus k, k factorial. So I'm just saying, hey, this next one is n. What's this one over here? So here is k equals 1. I'm going to do k in red here. This is where k is 1. This is where k is 2. I next got to figure out what's going on at k equals 3. And that's probably good enough here. So if k were 3 here, I would have n factorial over 3 factorial times n minus 3 factorial. And what does that look like? Well, n factorial is n times n minus 1 times n minus 2 times n minus 3, all the way down to 2 times 1. 3 factorial is 3 times 2 times 1. And then n minus 3 factorial is n minus 3 times n minus 4. We just keep dropping those whole numbers down until I get down to 2 times 1. And the cool thing about that is this and this cancel, and that would cancel with whatever's next, and those guys cancel. So the next coefficient is, let's see. Oh shit, I lied. I didn't want 3. K is 0, 1, and 2. We always count with 0 as the beginning of the binomial theorem. All right, so that would be the third one. All right, let's do that again. So I want n factorial over 2 factorial times n minus 2 factorial. Sorry about that. N times n minus 1 times n minus 2, and so on, down to 2 times 1. 2 factorial is 2 times 1. And n minus 2 factorial is n minus 2, all the way down to 2 times 1. And again, shit cancels. Bang, bang, boom, boom. So that long tail cancels. And my next coefficient is n times n minus 1 over 2 times 1. And this one over here would have been n times n minus 1 times n minus 2 times 3 times 2 times 1. So there's a definite pattern that evolves even with these, so you don't have to go through all this work every time. Okay, so we're getting there. All right, erase that for a second. So the next coefficient would be the n times n minus 1 over 2. And then the power of x drops again to n minus 2 h squared, right? The x power drops, the h power rises. And then this keeps on going, blah, blah, blah. And at the end, there's kind of the mirror image of what I see here. I'm going to get an n times x times h to the n minus 1, and then a 1 times h to the n. So there's a mirror image on the other side there. That's step 1 of my process. Step 2 is when from this, I subtract x to the n. Well, cool, I get to get rid of that right there. So that brings me down to step 3, which means take your f of x plus h minus f of x, which I get in step 2 by subtracting those guys, and divide by h. So I'm going to write that down. So I'm going to write all this down here. So I now have n times x to the n minus 1 times h plus n times n minus 1 over 2 x to the n minus 2 times h squared, plus there's a shitload of terms in between, and then it always ends in the reverse with n x h to the n minus 1. Oops, that's not a good n there. plus h to the n. And all of that has to be divided by h. And what I hope you'll notice here is that every single one of the terms above has an h, at least one h in it to give up. So two ways to think about this. I could factor an h out of the numerator, or I could drop each of these powers by 1. So that's what I'm going to do. So this simplifies to this h divides into that one. So I just get an n times, x to the n minus 1 plus n times n minus 1 over 2 x to the n minus 2. And instead of an h squared, I now have an h. And then zipping on down to the n here, n x h. This, again, divides by h, so that power drops by 1. So that's now going to be nx h to the n minus 2. And the last one, that power has to drop by 1, h to the n minus 1. All right, why is that power drop by 1? Because I'm dividing an h out. So I know no longer have a denominator, and I'm ready for step 4, which says take the limit as h goes to 0 of all of this. And the cool thing about that is this one has no h, so it just gets to hang out. And all of these other ones, h goes to 0, and if you multiply by 0, the whole thing is 0. So all of those suckers go to 0, and that has to be the derivative of x to the n. Oof, that was a workout. Holy crap. All right, good news. We never have to do that again because we have this shortcut rule we can just apply. So now we're just going to do a bunch of problems applying that. Take a deep breath, shake it off, and let's move on.